If you're ready to harness the power of your communications data, blast off with Nihilist today.
Hey, Blag. How's it going?
I'm doing fine, Ram. Thanks. How are you?
I am doing good. Welcome everyone to Coding with Nihilist. So in this live stream, we talk about programming languages, APIs, helpful application for developers, and today we're going to look at some algorithms.
Cool. So what's the main topic for today?
Yeah, we're going to spend some time exploring round-robin scheduling.
Nice.
And I started exploring this because we do talk about this inside of our scheduler. So we'll get to that towards the end of the video. And as well, we have a blog post on this as well. So it's at nihilist.com under our calendar API. So it's what is round-robin scheduling.
Mm-hmm.
And I want to walk through and talk about scheduling in general, because this actually comes from processors and how processors work. And then we can look at a few examples. So maybe we'll go through a visual. We can do a quick demo and a code walkthrough of what round robin is. Then we'll kind of close it off by looking at the scheduler and just how the scheduler can handle scheduling for multiple individuals.
Awesome. That's pretty cool.
Yeah, and we were going through this earlier, and you were able to name some of these acronyms much quicker than myself, but there are quite a few scheduling algorithms. And the idea behind them is when you have a processor or a CPU, it needs to be able to complete multiple tasks that are given to it, and it needs to decide in what order it needs to complete those tasks. So how does it slice up those tasks? Does it complete the first task that comes in, or does it complete the task in multiple slices? And that's what these different scheduling algorithms are. So RR is round robin. FCFS is
first come, first served.
There we go. First come, first served. So it's the first one in gets served. First come, first served. And the next one I think is schedule job next. So just scheduling the next job. So each job at a time. So there are actually quite a few algorithms that are out there. And for this video, we're just going to look at round robin scheduling. So for now, let's just jump into visual. We're going to go through a quick visual walkthrough before we jump into any coding. And this will give you an idea of how round-robin scheduling actually looks.
Yeah, it's always easier to see it in like visual way.
Yep, totally.
Topic.
So let me share my screen, and we can jump into this visual. So here are 3 different tasks that need to be completed. So we have process IDs. So we have an ID of 1, 2, and 3. As you'll see, we'll label them as P1, P2, and P3. And then we have burst time. And think of burst time as the amount of time that will take for that process to complete, or the calculated time for that process to complete. So here we have 10, we have 5, and we have 7. And when I mention time, think of it as units of time. It doesn't necessarily have to be seconds or milliseconds. It's just a slice of time that is represented within the processor. So if we scroll down, I'm just going to show you, we're going to go through step by step and walk through what round-robin scheduling looks like from a visual point of view. So here at the top, I just have the step number and have a time count. So this is units of time. And then I have quantum time. And quantum time is a representation of how long the processor will take, or how long the execution of a specific task is allowed before the next task is actually looked into. So here we're going to spend 4 units of time on each process before we look at the next process. So below I have a queue. So this is going to be where all the processes get queued up. And in our case, we only have 3 processes, P1, P2, and P3. So in the queue, we have P2 and P3. And in terms of process, we only have one process running, which is P1. So we're going to go through each of these steps and just take a look at what's in the process and what's in the queue, and just see how we actually get to a completion of these 3 processes. So going from step number 1, or step number 0 to step number 1, we notice that process 1 is going to take 4 units of time, and that's going to take away 10 minus 4, so that's going to leave us with 6 units of time. And from there, we have process 2 that's kickstarted. And the next process that's going to run is going to be process 3, or P3. So if we go to the next step, we'll see here that now we have P1 that's waiting next with 6 units of time remaining. And we have P3 that's kickstarted. And P2 has gone back to the queue which is going to have 5 minus 4, which is going to be 1 unit of time remaining. So this is at t equals 8. So going to step 3, process 3 is going to complete. So it's going to be 7 minus 4 units. And process 1 is kickstarted. And process 1 has 6 units remaining. And next up in queue is P2. So if you think about this programmatically, we're going to have two different lists. We're going to have a list of what's in queue and what's being processed.
Yeah.
And if we continue moving forward, we'll see that P2 comes up next. And P2, since P2 only has 1 unit of time remaining, P2 will actually finish at time of 17 units. So we have time of 16 units.
Mm-hmm.
And now when we get to step number 5, this is when time equals 17 units. Process 2 is now completed.
Yeah.
So we're just taking one item at a time off of the queue, completing it for 4 units of time. And if the process completes before that time, we just start on the next process.
Perfect.
So here we have process 3, which starts at step number 5 at t equals 17 units of time. But we know process 3 from before only needs 3 units of time to complete. So if we look at the next step, we'll see that process 2 and 3 are completed now, and only process 1 remains.
And the queue is already empty.
Yeah,
because
the
we don't
queue
have
is
any
empty.
processes. Perfect.
Yep. And this is more of a generalization. I don't think it would make sense for a queue to ever be empty in a processor's life.
Yeah.
But just for simplifying the example here, we only have 3 running processes.
Yeah.
And as we see in the last step, the queue is empty. There's no more processes running, and we have the completion of process 2, process 3, and process 1.
Okay. I see.
So just to highlight, process 1 completed at t equals 22.
Mm-hmm.
Process 3 completed at t equals 20, and then process 2 completed at t equals 17.
Nice. So 17, 20, and 22.
So when we jump into the demo, we'll see that these time slices or these time units will show up in the actual code that we created. But before we jump in, please like and subscribe. We'd love to hear your feedback, thoughts, or comments on any past videos or any upcoming videos that you'd like to see, whether it be building with Nihilus or even any other APIs that are out there.
Yep.
Awesome. Let's jump into an actual demo. So let me share my screen and we'll take a look at a demo. So I'm going to run this code and we'll take a look at what it does, but it's very similar to the actual visualization that we had where we have 3 different processes running. So once I run this code, it's going to run through and process each of the 3 processes, and it's going to show at what time unit or time slice was it completed. So here we have, as we saw in the visual, we have process 2 was completed at 17 units,
Mm-hmm.
process 3 was completed at 20 units, and process 1 was completed at 22 units. Let's take a look at the code, and then we can come back and run this one more time at the end.
Nice.
So at the very bottom, we have run round robin, and it's going to take in 3 processes. And for these processes, all we're doing is we're actually creating an object that contains an ID, a burst time, which we've mentioned before as the estimated time for completion of an actual task, and as well the remaining time. So we're going to store the remaining time of any one of these processes.
Mm-hmm.
So we take this information, we're going to pass it into round robin. So we're passing in an array. So think of this as your initial queue
Mm-hmm.
of all the processes. And as well, we're going to pass in the time quantum. And this is the actual slice of time or the time units that a processor will spend on one individual process. I'm realizing I'm saying process so many times. So another way to think of this as each process is one individual. So we have 3 different tasks that the processor needs to run through and complete.
Yeah.
So now let's take a look at run round robin. So what we do in this function is we're actually taking in the actual tasks and the time slice to complete them, or the time quantum.
Mm-hmm.
So the time quantum being the amount of time allotted for each process in that sequence for completion. We copy over the processes into a queue. So we're creating a queue. So this is an array that's going to contain each one of the tasks we want to complete. And then we're going to store it in an array called completed. So we have an initial variable, and this variable is just going to store the actual timestamps. So we can print them out anytime we want to.
Okay.
So here, afterwards, we have a loop. And what this does is check if there's anything in the queue. If there is anything in the queue, it's going to go through and actually complete that process or complete that task. So we grab the first thing in the queue.
Mm-hmm.
We're going to calculate the time to actually run that item. So this is going to take the actual remaining time and the actual total time allowed for one slice of time. So whether it be 4 units, which we have in our example, and it's going to determine the time to run. So we're going to subtract that from the remaining time, and then we're just going to accumulate the actual total time. So if the task is, for example, 3 units of time and our time quantum is 4, that means the task is actually going to complete within this execution of the cycle or this execution cycle of the processor.
Mm-hmm. Cool.
So here we have a check if the process is actually completed. So if the remaining time is 0, what we're going to do is we're just going to log out that the process or the task was completed at that time.
Mm-hmm.
And we're going to add it to the completed queue or the completed array. Otherwise, we're going to say that the process has run for a certain number of times, and we're just going to add it back to the queue to continue processing.
Nice.
So just to run this again, we have the 3 tasks which we've seen before. So here are the three different tasks. So we have process 1, process 2, process 3. So these are the IDs, and then we have the burst time of 10, 5, and 7. So running this in the terminal, we see that each process is run, and then afterwards the processes have completed in the order of process 2, process 3, and process 1.
That's very nice. And I have a question on your source code, because
Yep.
I'm not a JavaScript guy, so
Let's take a look.
something caught my attention. So if you go a little bit up,
Yep.
a little bit, so there. So when you have the constant QE and you're passing between brackets 3 dots and processes, you're making kind of like a deep copy of the array, right?
Yeah, this is a duplicate. Just creating a new copy.
Okay.
So we're just using the spread operator here. And what this does is it takes the existing array and then spreads it across the queue.
Okay. That's something else. Okay, cool. I was just curious because I have never seen that in any other programming language. So. Okay, cool.
Yeah, this was added recently in ES6 to JavaScript, where you can use like the spread operator to spread out a list or an object within another list or an object, respectively.
Okay, I see.
And now this kind of leads to the next thing. Our actual scheduler has similar concepts of round-robin scheduling. And I just want to show the different algorithms or concepts that we use. So I'm going to share my screen again, but we're going to look at 2 different algorithms that we have. So it's availability and it's fairness. So let me share my screen again.
Sure.
There we go. Boom. Okay. So on the actual scheduler documentation,
Nice.
we have 2 different algorithms, and the way I'll describe this is we have maximize availability and then we have maximum fairness. So let's take an actual example of a physical therapy clinic. So you're going to have many physical therapists. And if we were to choose maximize availability, what this algorithm would do, or in this scenario, what we would do is we would actually take all the physical therapists and take their availability. And if one of them is available at any one of those time slots that we want to show to the user, we would show it to the user. So the user would see all the availability for each time slot, regardless of which physical therapist is being booked. So the idea here is that we want to show as much availability to the user. And the way to look at maximum fairness is we want to go through and see which physical therapists are not booked as often. And we want to be able to bubble up their availability first. So we would look at which physical therapists are booked, which ones are booked more often, and then we would take the least booked physical therapist and show them to the user.
Uh,
And the idea here is to actually spread out the availability or spread out the bookings across all physical therapists.
mhm. So they got the same chance of being booked, right?
Yeah, yeah.
Nice.
So the algorithms are slightly different, but it's also depending on the user experience. What experience you want to give to either the individual's booking or the individual's offering up their actual calendars and availability. And just before we jump into anything else, I just want to plug our blog. Go to nihilist.com/blog to check out any and all upcoming content that we have. We recently released some content on building with the Nihilist scheduler using iframes.
Yep.
So go ahead and check that out. Some great content on how you can actually communicate with an iframe to your actual application. And this is very common across the web when you're building with multiple tools and integrations. So go ahead and check that out.
Cool. Oh, nice. So we have a new schedule for our live streams. We go every Wednesday and Friday at 2 p.m. EST, 11 a.m. PST. So you can wake up a little bit later. Yeah.
So you can be all fresh and ready for our live streams.
Yeah, exactly.
This topic was definitely challenging to go into, but I'm glad we got a chance to talk about it before we start looking at implementation. But I also want to say, no, some of Blog's topics in the morning can be very challenging as well. Fun and challenging, but I'm glad we have this later time. So again, it's 2 p.m. Eastern and 11 a.m. Pacific.
Yep.
So Blog, what are we going to talk about next?
Okay, so you see, Ram, how we always say it, like this live stream is about programming, APIs, and more. Well,
Yep.
here comes the more part. So we're gonna talk on Wednesday is how to model a simple scene using Blender. Blender being a 3D modeling software which is open source and amazing. So we're gonna do something pretty low poly, but at least you're gonna kind of like sense the basics of using Blender. And the first time you see it is kind of like scary, but you're gonna see that it's not so much. So
Sounds good. I'm looking forward to it.
Mhm.
Awesome. Well, that's a wrap for today. Please go ahead and follow us on LinkedIn, Twitter, even on YouTube. Subscribe to our videos, and that's all. That's all for me.
Yep, for me too. Just mention that don't forget to go to github.com /nihilist.samples where our code samples reside. All the code samples for the blogs and the live stream are going to be there. So just go check it out. And yeah, I think that's it for today. Great topic as always, Ram. Always a pleasure to live stream with you.
Awesome. Thank you for joining me. Bye,
Thanks.
everyone.